However, in this video, we will solve example 4.3 from the book Applied Thermodynamics, McConaughey and D. Stopes. Here is the statements. Air at 15 centigrade and 1.05 bar occupies 0.02 meter cube volume. The air is heated at a constant volume until the pressure is 4.2 bar and then cooled at a constant pressures back to the original temperatures. Calculate the net heat flow or from the air and the net entropy change. Sketch the process on the TS diagram. Okay, so we have air at a temperature. So what is the temperature T1? That is 15 centigrade. If you convert that into Kelvin, just add 273 with it and you will get 288 Kelvin. Next is the pressure P1, initial pressure, that is 1.05 bar. If you want to convert that into Newton meter square, just multiply this value with 10 power 5. So it will be converted into Newton meter square. Remember, all your values should be in the SI unit so that you get the correct answers when you are doing calculations. Now the air is heated. Air is heated at a constant volume. So until the pressure reached up to P2. So at a constant volume, the air that is heated at a constant volume such that its pressure reached to 4.2 bar. So if you want to convert that into Newton per meter square, that's very simple. Just multiply with 10 power 5 is Newton per meter square. Now the statement that we have read now, we want to convert that onto TS diagram. Remember, this is the pressure line for 1.05 bar. This is the pressure line for 4.2 bar. So what he says, it says that at a constant volume, when it is heated, the pressure rises from 1.05 bar to 4.2 bar. So at a constant volume, when the air is heated, its pressure increases up to 4.2 bar. So this process will follow from line 1 to 2 at a constant volume. This is a constant volume line. This is the pressure 1.05 bar. This is the line of the pressure 4.2 bar. So when you are supplying the heat, actually you are increasing its pressure. So at point 1, its entropy will be S1, and similarly if I drop its value, that will be S2. Now from 2 to 3, the heat rejections are taken place at a constant pressure, that is 4.2 bar. So it will follow this line until the original temperature, that is 15 centigrade, is reached. So our process follow the line 1 to 2 heat addition, then 2 to 3 heat rejection. So this is heat additions taken place in this process 1 to 2, and from process 2 to 3, this is heat rejections. Now let's come to its solution. Before solving this example 4.3, you will need CV value, that is 0.718 kilojoule per kg K, and CP value, that will be equal to 1.005 kilojoule per kg K. These are constant for constant volume and constant pressure for gases and air. and another more important constant, that is R, that will be equal to 0.287 kilojoule. And one more thing, the volumes that is given is 0.02. So the volumes that contain this air is equal to 0.02 meter. First we need to find the mass, that is equal to PV is equal to mRT. So if you simplify for mass, you will get PV divided by RT. Now put its value, you will get the mass. So what is pressure? That is initial pressure 1.05 multiplied by 10 power 5 multiplied with the initial. So the volume, that is constant, that is 0.02 divided by 0.287, that is in this. So to convert that K into number, just multiply with 1000, multiply with temperature, that is 288. So after simplification you will get its mass, that is equal to 0.02 kg. That is the mass that contains in this volume. Okay, next we need to find the temperatures T2 at this point. We need to find the temperatures. So what will be the temperatures? We need to find it. So we know that P1 divided by T1 is equal to P2 divided by T2, because at a constant, so from process 1 to 2 volume is constant, that's why we apply this formula. Now expression for T2 will be, that is 4.2 divided by 1.05 multiply with T1, that is 288. The final value of T2 you will get, that is 1152 Kelvin. The next things we need to do to find the heat that is added from process 1 to 2. So the heat that is added from process 1 to 2 is equal to mass of the gas. So it's a constant volume, we will write CV, and change in temperature, that is T2 minus T1. Mass is 0.0254. CV value is constant, that is 0.718 multiplied by temperature is 1152 minus 288. After calculations you will find that the heat that is supplied from process 1 to 2 is equal to 15.75 kilojoule. Next we need to determine the heat that is, so from process 2 to 3 heat rejection is taken place. So we need to determine the heat that is rejected from process 2 to 3, that is equal to mass, constant pressure value, and that is T1 minus T2, T3 minus T2, and T3, the value of T3 is 15 centigrade, because the coolings are taken place till that gas comes to its original temperature, that is 15 centigrade. So the temperatures T1 and T3 that are same, that is given in the statement. This mass, that is 0.0254 multiplied by 1.0. I'm just adding the value, that is 288 minus 1152. So the final value you will get, that is heat that is rejected from process 2 to 3, that is equal to minus 22.05 kilojoule. So the net heat that is we obtain in this process 1 to 2 then 2 to 3, just do the subtraction of these equations 1 and 2, you will get the final answer of the net heat, and that is equal to minus 6.3 kilojoules. So it means that the net heat is rejected, not added. Next thing we need to find is the entropy changes. Now come to the process 1 to 2. The entropy change is S2 minus S1, and that is taken place at a constant volume. So the entropy change is equal to change in heat divided by temperature, equal to mCV, because at a constant volume the process 1 to 2 is taken, and then change in temperature divided by T. So I can write that S2 minus S1, that is equal to mCV dt 1 over T. If you apply the integrations, and the lower limit is 288 and the upper limit is 1152, so apply the integrations, then next apply the limits, you will get the value, and the expression just look like this. So that is S2 minus S1. What is the m value? That is 0.0254. What is C value? That is 0.714, and then after integration apply the limits. The upper limit is 1152, limit is 288. So after simplification you will get the change in entropy from S2 from process 1 to 2, that is, so after simplification of these equations you will get the value of S2 minus S1, that is 0.0253 kilojoule per Kelvin. Here is equations 3. Now we are doing to find the entropy change from process 2 to 3. Remember, the process 2 to 3 that is taken place is at a constant pressure line, so that's why we use the value of Cp instead of Cv, because it's a constant, is taken place at a constant pressure line, that's why. And it's a cooling process, so then we will see its corresponding entropy change as well. So at point 3 the respective entropy, that is S3. So the change in entropy in this case from 2 to 3 is S2 minus S3, and change in heat divided by temperatures, so S2 minus S3. So the change in heat, that is mCp, and change in temperature, that you can write T1 over T. Apply the integration to find its value. The lower limit is 1152 and the upper limit is 288 in this case, process 2 to 3. So you can see that the upper limit is T2, that is 1152 Kelvin, and lower limit, that is 288 Kelvin, and that is T3. So we have applied the integration limits. Now after integration we apply the limits, so the S2 minus S3 will be equal to What is m value? That is 0.0254. What is cp value? That is 1.005. And now apply the integration, then apply the limits. So integration is ln, the upper integration is 288 and the lower is 1152. So after doing these simplifications, you will get its value, that is S2 minus S3 equal to 0.0354 kilojoule per Kelvin. Now we call this equations 4. Now subtract equation 3 from equation 4. So we can write that S2 minus S3, we are subtracting equation 3 from 4 minus S2 minus S1 is equal to, if you subtract this value from this, you will get the value, that is 0.0101 kilojoule per Kelvin. So this S2 will be cancelled out with S2 and this minus minus become plus, so I can write S1 minus S3, that is equal to 0.0101 kilojoule per Kelvin. So this is the final change in entropy in this example 4.3. I hope you understand the concept and example 4.3. For more such video, please subscribe my channel.